How's it going, everybody?
That's it.
Welcome back. I'm Philip Ong. I'm here with Dane DuPont. We're going to be doing an update for you guys on the 10th day of the Kīlauea 2020 Summit Eruption. I'll be doing some narration of the videos and data, and Dane's going to be manning the live chats and gathering your guys' questions and passing them along, so we'll have a couple question breaks as we go through. But we're going to present to you guys videos and data from the USGS Hawaiian Volcano Observatory and try to kind of break it down and in a way that you can understand and maybe make a story out of it so you guys can kind of follow along. So that's our goal here tonight. So anything you want to add, Dane, as we start off our broadcast?
No, just thank everybody for joining us. We're coming to you live via Hawaii Tracker on Twitter, Facebook, and YouTube.
That's right, hawaiitracker.com. And so we'll start by showing you guys this video of the lava plunging into the filling crater, right? There's a lava lake that's fed from above by lava plunging in from the wall, and you can kind of see, if any of you guys have been following and saw like Fissure 8, how much it was, how gas rich and frothy and it was at times. This does not look like that same kind of stuff. It's kind of gooey. It's definitely hot flowing lava. There's a lot of bubbles. You can see them kind of, if I look at the area right in here, I can kind of see different pieces of crust, right? Some of which are actually bubbles forming on there and breaking the crust apart. So there's definitely gas in there. You can definitely see the lava liquid enough to form that crust and ooze its way through, right? So they're saying here in a caption that the lava pours out of an opening that's 4 to 6 meters wide. That distance, 4 to 6 meters wide, 4 to 6 yards across. And so remember, we're looking at this with a giant zoom lens from a huge distance away from the top of the crater through the USGS camera here. Thank you, USGS media team and photographers, for giving us this really insightful view. You can kind of see how the lava is forming that crust right away. It's almost starting to form little ropes. You can kind of see these kind of circular pattern going on here, right? As the lava plunges into that pool, and it's kind of filling. And that's kind of one of the things we're going to talk about today, is a different, how lava isn't just lava, but it can be more bubbly or it can be more dense, and how that might actually matter as far as eruption progresses or doesn't progress. We'll have to wait and see what actually happens here. So that is the lava pouring in, and let's delete that and show you guys now a helicopter overflight of Halema'uma'u I was taken this morning. This is the first view. You can see the old Trina Crater's road right here plunges off into that lower piece of land right in here, and I think as we come over the edge you might see another piece of it down here. There's a piece right in there and some more of it right in there. Trina Crater's road. And of course, our big pit crater, Halema'uma'u, that's inside of Kīlauea caldera, which is this larger thing all the way out here, a larger crater all the way out here. And there's a lot of information here. Kind of go through it one more time so you can kind of make sure you catch all of it and not rush through anything right here. Yeah, you can see these big cracks that formed during the summit collapse. There were a lot of cracks here before, but a lot of them opened or widened or actually allowed big blocks like this to drop down. So there's our lava lake. Here's our western vent putting out a huge gas plume, right? It doesn't seem that big, but that's where all the gas is coming from. No gas directly visible coming from the east or really bubbling from anywhere else on the surface of the lake. If you guys notice that, I really don't see gas bubbling really that anywhere else. Really, this is like a big chimney right there. So maybe I'll pause it and rewind it here so that we can kind of look at things a little bit more static here. And then you can also see this big island raft. We can talk about the different things we've been calling it here as we go a little long further in our broadcast. But that thing is still in there, floating around, reportedly rising with the rising lava level, right? The lava level last broadcast we made, you guys, last update we gave you guys a couple of days ago, the lava level had kind of stabilized. It might have even dropped a little bit. And then since then it's resumed a slow rise, and we'll show you guys that in the data coming up as well. It's not very fast. You expect to slow down because the crater gets wider the higher up it goes, right? Kind of across this way, it's wider the higher up it goes, the more it fills. But also because it seems like the rate went down a little bit too. So we'll see about that. All right. So one other thing to note is clearly there's a lot of black crust forming on this lava lake, right? And that crust maybe is part of the reason that you don't see so much gas, or, I don't see, it's hard to see from this angle, but see any kind of emissions coming off from even from the cracks in the lake and other places. So we'll keep an eye on that as we work our way through our update here. And let's that one too. And show you guys another video. This one came via Ikaika Marzo, who posted from Volcano Helicopters, who are the guys who fly with the park. So here's a video similar. This is a piece of the Chinnakuras Road that's actually in a block below. Here's that upper cliff, right? And so you can get a little bit closer view of that western vent, that crust, the island, Raft, and then that northern vent that's now just like a feature on a wall, and you don't really see any emission or any kind of drain or flow feature on a surface going towards it anyways, right? It seems like the lava is probably flowing back in there at some lower depth, right at the bottom of that vent, where you can imagine wherever it's been drained down from the beginning could probably just wear its way through and actually physically carve out a slightly bigger hole. So that's the easiest place for it to drain. Maybe the surface isn't seeing that so much, and it's getting that crust effect, and it's hard to see that with the scale images that we have right here. So that is the intro video I wanted to show you guys. We'll come back to this thermal video here in a little bit, but we're going to switch over to the webcams here and look at the view from earlier this afternoon here at the summit. I kind of wanted to give you guys a daytime view after evening has fallen here in Hawaii. So you guys can see there's a little bit of gas, but not nearly as much gas as we were seeing in the first few days of the eruption coming out. And that was the thermal camera image earlier today. So let me reload it here and show you guys thermal image now. And so you can kind of see that right in here are our western vents, and they're pouring in. You can't see as much flow on a surface. All that stuff's kind of tubed in. We'll show you guys that here shortly as well. But there's kind of a flow going that way, and it appears there's a flow going this way. Although at times it seems like this thing might counterflow a little bit too. And in any case, we have all these spotted little islands. I believe it was something like over 10 of them that were counted by USGS. I'll have to look at the update to refresh myself on that. But that kind of northern vent over here may be where lava is draining back in, kind of not right at the surface, but a little bit deeper down within the lake. So it's kind of hard to tell that exactly. That's one of the unknowns. And a little later, towards the end of our broadcast, our historical segment, we'll cover how the history of islands in the summit lava lake and past summit lava lakes of Kīlauea, how they changed, and some of the fascinating things with that as well. So if you guys are into that, then stay tuned. So kind of scrolling back up here, there is glow still. The glow may be reportedly not as strong as before, but it's definitely still glowing. Of course, there are other factors as well. You can see the nice clear sky. So that maybe makes the glow more visible from other areas around the caldera for those who have gone to visit tonight. All right, so that's kind of what's going on there, and let's look at the actual animation provided by the USGS as the first step of reviewing what's been happening thermally with a filling lava lake down here. And I'll just give it a second to load here. And there it is. And one thing you might notice is that at times this area down here might seem brighter, and other times might seem a little less bright. And it's hard to kind of gauge with a scale that's up here in the top right. But it seems like there are times when it might be slightly more luminous in a thermal image, right? And of course, the camera is also dealing with the gases blowing in front of it and getting between it and making the image blurry sometimes, or obscuring or changing the measurements. So that's another factor to consider as well. Okay, here's our most recent thermal animation from the USGS. The last 24 hours from the F1 cam. And it does seem like there's like a flow going off in both directions like this. And then because of the islands, or maybe at some point in here, they are diving down and flowing back. And that would kind of help support the idea of the island getting pushed this way, right? Because the island has a big area of it that's underneath the lava as well, right? And we're not unknown exactly how much, but certainly some. And it's that bottom part that kind of acts as a rudder historically, and so the current, like at a lower down, maybe it was actually pushing it, even if the surface level is going around it in the opposite direction, right? That's kind of the interesting thing about it, right? It's actually telling us something more about the deeper current, and that might be why it's useful to have such a big island that might have such a possibly a large root to it, right? At least I'd imagine something akin to the bottom of the crater it formed in. And we don't exactly know what this thing is made of. But some things that have been documented in the past are that, you know, rocks that have a lot of water in them, and then they were to fall into lava lakes, would actually form bubbly lava around them, and then those things could possibly act as floats for the island. And it kind of makes a veneer, like a rind, and it can have floats attached to it that kind of help buoy it up. And then as it kind of keeps degassing, it can kind of add more bubbles and things as well. So there might be something like that going on. No one exactly knows. There is one fascinating example where one of these islands kind of flipped over, and her picture is taken. I'll show you guys that later on. So, but that's kind of the view for the last 24 hours here from USGS. You can see that this big island is moving back towards the plunge spot right here, right? It's kind of mostly too big over, you can't tell from this angle. And so, in fact, let me switch over to the next. This image was just released by the USGS earlier tonight. And this is kind of a comparison. You guys can see December 21st on the top left, where, let's zoom in. Let's do these one at a time for you guys, since we have all this screen. December 21st, we have upper west fissures, we have lower west fissures. By this point, that central fissure kind of died off, but it had an upper and a lower part that was kind of in that lower block that had fallen into the pit as well. And we also had the much more vigorous north fissure, right? You can kind of tell from this, the vents got some height to it there. So what we're seeing now, the lava level all the way up to here, even if we see the kind of spatter up above it here, there's still quite a bit of hole farther down in there for the lava to be draining back into. And that's kind of what we would imagine something like that's happening. And of course, it could be draining out through that puka, right, that hole, and the one that's possibly down there, that one may be less likely, and possibly also through this one down here. So there are a lot of submerged spots now for lava to be draining in, and you know, it may be that there's more draining possibly than it might be slightly out of balance, right? So you basically have no shortage of pathways for this lava that's collecting in this pit here to drain back. And so back in December 21st, we can kind of see this is the second day of the eruption. Our island was there from the very, very beginning. You know, as soon as the steam cleared, the island was there, kind of floating in this pool of rising lava. And so we imagine that had something to do with that formation of lava plunging into that lake of water that was there, right? And for you guys want a quick recap on the history of the water, just very, very briefly. The last collapse of the summit caldera, I believe, was August 4th, 2018. It was not quite, almost 1 year later, end of July 2019, that photographers first spotted what looked like puddles, water reflections of water at the bottom of the pit. And then over the course of a year and a half, that lake has been rising, you know, just a little bit at a time, and kind of it's been fascinating to watch that, you know, you can look in our past updates how that water filled all the way up to a depth of 50 meters, right? So somewhere upwards of 160 feet, right? So that water interacting with the lava pouring in there, and that frothiness, you might have had that similar effect of making some very frothy rocks that trapped, whether it's air or gas or steam, you know, any combination of what kind of gases in there. And that somehow, if that had any part of that fused together, then that could be what's, you know, giving it some buoyancy in there. And one thing that happens is there's kind of the lava kind of freezes on the outside, and it kind of makes an insulating rind. And so that middle is getting hot. And that island, people were asking, like, well, you know, like, shouldn't it sink sometime? And like, shouldn't it melt? And the answers historically are, well, if it's in there long enough, it will sink and it will melt. But if this is a process that doesn't happen right away, it might take months for that to happen. So if we have a lava lake with a thing floating around, then possibly you could talk about the thing, you know, doing these crazy features that we'll discuss later that were the case, you know, over 100 years ago here in Kīlauea. So December 21st here, and let's move to the next frame, December 22nd, and there is the island / raft, right? So kind of discuss why, you know, people were calling it islands, people were calling it raft. Some people imagine that, you know, we might have both opinions, you know, in every discussion, right? Perhaps even at USGS, an island might be something that's actually rooted on Earth and the liquid rises up and around it, whereas a raft actually floats around. So if you don't care for that, you know, to be that picky about it, you could call it a floating island, or a rafting island, but it really doesn't matter. So when you guys are hearing raft or island, you know, or not, it's not an island, it's a raft, and you know, that's kind of where we're coming from. You know, just like before when we had a pond of water and then it was a lake of water because we had to go by the definition of pond versus lake, and it had to be deep enough you couldn't see into it and see the bottom and all those other things. So anyways, not to get lost there, right? But you know, there's our island / raft. So by this point, the lava level is rising up. Most of the lava is coming out of this north fissure, the main fountain, and you can see it's already almost to that bottom level of the vent there. We've completely drowned that middle vent and lower vent of the west fissure, and just the upper parts remain, right? And it's coming out of a trickle, and this thing is a vent that actually deactivated. It kind of became intermittent, then deactivated before reactivating once the vent drowned the northern vent. The lava drowned the northern vent, essentially blocking it, apparently, you know, and that's when we saw a change in the monitoring signals that the inflation began. So the whole pressure balance changed there once that drain back took over, right? It must have been draining back for longer than that. It just finally reached some tipping point where there was enough stuff that was colder, right? Cold for lava, in the sense that it's had a chance to let off some heat through venting at the surface of the lake, right? To let out some of the gas. So it's denser, it's colder for lava. And so it can go back in that hole, and it might be able to push back with enough pressure to stop any gas coming up that way. And so there's not, I mean, the crack isn't just a single, very even crack. It's got lots of different branches to it. So the gas is just going to find another way to go out. But that might require like having some back pressure coming down some of these other pathways to allow the gas to kind of work its way efficiently to the hole where it can actually come out, which is only one of them, series of those left. So a few days ago, we saw this west fissure take over. As that happened, and lava was streaming down from 3 different open holes. And we kind of saw that as the lava was cascading down this little ramp, this little lava delta was building for itself. It formed essentially a little channel that started to crust over and encase itself, essentially forming little lava tubes. And so in this last image here, December 30th, USGS shows an image from today. This is taken from the opposite point of view from that thermal camera. The thermal camera that we're looking at, time-lapse, is looking in that direction. So this fissure is the same one as kind of at the very bottom of our field of view. But in this, from the helicopter, taking pictures from the other side, they can actually then make the maps that they're releasing, and also release this kind of alternate point of view. So you can kind of see that there's still vents in there. Clearly, right in here, there's lava plunging into this thing. It's hot, right? Very clearly. And so it's coming. There's 3 kind of glowing holes still, and lava is just kind of going up out of the crack and down through this little, I'm not sure what, it's almost like a little kiln or something, right? That lava tubed over lava delta, like within the edge of that pit. And it's plunging in clearly right there, and that's driving the circulation. So all the lava is still coming out. I mean, it might not look like it necessarily, but it's coming out and plunging in through this little area right down here, and you kind of see it's going around that way and that way, and you can kind of see it's making some of these pieces of crust are actually getting pretty purple there, which means cold. So there's some pretty cold pieces of crust, kind of with hotter crust in between them, right? So it's interesting that you actually have, you know, at times the circulation seems to stagnate enough that you're forming these big chunks of harder, more solid crust, and then apparently the flow increases in some way where it then is able to break apart, right? Or, you know, something from below, heat, and possibly the gas, because, you know, there's gas, small gas bubbles in the lava everywhere. So it's just a matter of, you know, how like small bubbles and the big bubbles all kind of work together. And so it's coming up here, and you can kind of see breaking apart these pieces of crust by showing these brighter edges right there, right? So the darker spots here are the smaller islands. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, plus the big one right over here. And we'd imagine that at some depth, you know, like basically the lava is coming around this way, and it seems this way as well. There's some blockage right here, right? It seems like this small island is getting pretty close to the vent over here, so that's interesting. So I mean, you know, maybe there is some draining happening just below the surface level in that direction over there, while in the middle, the flow kind of comes this way, right? And dives down and over that way at a lower level, something like that. And then who knows what's happening underneath this side over here, right? That there's, there's kind of a big question mark as far as circulation goes. But that's what we know. So there is a USGS image just released tonight, that 4-panel comparison. And we'll get to some questions here shortly, but let me kind of finish out this first little segment here and show you guys this plot that USGS is putting up. Let me give it a refresh here because there may be some more data that pops up as I update this throughout the day. This is a graph showing the depth of the lava lake at Kīlauea Volcano Summit. So there it is. Kind of break it down for you guys. Let me maybe zoom it in a little bit here. And so this is the early filling phase right through here. And I'm not sure why there's a lot of variation in these measurements, but you can kind of, imagine it was maybe a more chaotic time there at the beginning, right? And there's another little bump right in here as well. Maybe that's I'm not sure what that exactly is there, but essentially at the 26 right in here, that's kind of when we switched. That's when we switched our vents. So let me see if I can change my color here. Give me a better color right there. That's when we switched from our northern vent to our western vent. And at that point in time, the northern vent started to drain. So we saw the lava level going down for a while. Right, and the western vent was still erupting, but it wasn't keeping up with the draining, it seemed like. This is not much. We're talking about an order of a few meters. Right, so we're talking about an order of maybe 6 or 8 feet or something like that. But you can see that beginning on the 27th, coming in the 28th, we started seeing the lava levels build back up again, kind of picking up to where they had been at that 179 kind of mark was kind of the high point before, and so kind of came back up to that again on the 28th before actually surpassing it, right? So now we're above the 180 mark, although you do see this kind of effect where it's going up and down and up and down and up and down and up and down, right? And so that's something that we'll see if we can see in some of the imagery as well. And it might just be a matter of like there's more lava coming into the pit, or lava coming into the pit is frothier, and then there's less frosty lava coming into the pit, or more frothy. It could be something like that, right? And so it's kind of just depending how the draining and the frothiness and all that stuff, interacts. Those are the fascinating things to think about that may be causing these variations on the short term within this plot here. So, but generally the trend in the last 4 days has been up, right? We can see that, even if it's a slow up, right? By slow, I mean, let's compare the rate here earlier of this thing rising. This thing earlier was rising at a rate something like that. Here, let's see if I can do a little better. This thing was rising at a rate something like this. And then more recently, it's rising at a rate something like this. So rising, but at a slower rate, right? That's kind of what we can see there. Right. And we have the volcano update. It's going to be the next thing we cover. So get all the actual details of the lake here, and then this is kind of the last thing to look at. So we have now, as of 3 a.m. this morning, 181 meters, 593 feet deep, with a narrow black ledge, reduced but still elevated. SO2 emissions were measured on Monday, so no new reported measurements. The most recent measurements on Monday, though, were 3,300 tons per day. So that's lower than the 5,500 and 5,000 tons per day, or the last two before that. But as Dane actually first pointed out, and we're also hearing this now, this is in line with the emissions, the long-term lava lake from 2008 to 2018 at the summit of Kīlauea. So like the background threshold of a long sustained eruption is about where we are. So, we're not seeing it drop below that yet. And if we were to see that, it might be a sign that the gas is maybe reduced in some way different than it was in 2018, right? And that's kind of one of the fascinating things, is to kind of figure out why ultimately, how much the magma recharging the volcano, how fast it's coming in, how often, how hot, by the patterns that it's putting out to the surface through all these different events. So seismicity remained elevated but stable, with steady elevated tremor and a few minor earthquakes. So the steady elevated tremor is something we'll look at a little more closely. It is elevated everywhere, but kind of can be elevated more, elevated a little less, right? So, and we have the same kind of observation about the East Rift Zone going on here. That magma, they infer magma is moving into the summit from the rift zone, and that nothing is actually going on in the rift zone apart from essentially adjustment from the lava moving out. So the most recent numbers, 5.2 billion gallons, that's 30 million cubic yards or 23 million cubic meters. Right? Dimensions of them, 770 meters by 490 meters or 840 by 535 yards with an area of 29 hectares or 72 acres. Dan, you want to chime in here and give us that in feet?
Yeah, that's an interesting one. Is 840 yards is exactly 7 football fields if you include the end zones, right? Both end zones, 120. So yeah, it just to get the conceptual wise, take 7 football fields, put them in a line. That's the wide part of the lake.
Yeah, that's quite a distance there, right? For the whole lake. And then as well, they have measurements on the island, right? So they actually talk about the island drifting slightly to the west and rotating counterclockwise. The 10 smaller islands to the east remain stationary. At the time of this writing was 8 a.m. this morning. The main island measured 250 meters, 820 feet in length, 135 meters, 440 feet in width, and about 3 hectares or 7 acres in area, right? The island is 7 acres large, based on the December 28th thermal map. And they're also showing the island surface to be 6 meters, 20 feet above the lake surface, right? This is something interesting to see if they actually will give us repeat measurements of this, or after everything is all said and done, that they publish that, right? Because that's one of the things that can help us figure out the buoyancy, is we essentially have a bob, which is the island in there. It's just kind of adjusting to the level of rising and falling. And so something that can happen is if you replace frothy lava that's taking more volume with slightly less frothy, denser lava that takes less volume, then the island will actually float the same, and it'll appear that the level will go down relative to the island, but the island will actually kind of just stay in its same place. So there's some fascinating things you can figure out. If the island's actually rising up with the lava level, then you can say, okay, then that actual lava frothiness is similar to what's already in there to actually be able to lift it up with it as well. So there's kind of some really interesting dynamics there to kind of go into detail for you guys who like to do this kind of thought experiments. So let's just finish up this update here, and I'll just do today's because it's kind of encapsulating what was said yesterday as well. And so that's basically it for the update. That's given in writing every day now by the USGS. And so one thing I want to point out with the gas here is just kind of is our measurements now. Our most recent measurement here is at that 3,300 compared to 35 or 5,500 and 5,000 right in there. So we talked about before, this essentially is giving us some kind of curve. It's going up something like this, right? And the question is all about how long it's going to tail off here at this right end, right? Because as we've compared before, there are different ways that this, if our long-term eruption rate drops and we end up having a sustained long-term eruption with a lower eruption rate, then we can have this kind of long tail version, right? But if eruption rate stays high, moderate to high, then we might expect it eventually to kind of tail off, even if it does draw out a little bit in time, more so than just the pure bangers that come in strong and go out strong too, right? So Dane, I think we're ready for our first round of questions, and then we'll kind of look at some more interesting things from there, and we'll probably be asked about what we're going to talk about next, but let's have at it.
All right, let's jump right in then. Question from YouTube. We did answer this one before, but it's always good to, catch them again. Has the USGS been able to obtain a sample to see if this is a continuation of the mantle plume or more of the older stuff from 2018?
So great question. We did answer it before. As of that time, we had not heard of any samples being collected, but since then we have had report from USGS that they have collected samples of tephra and they are currently analyzing them. So no results yet. So hopefully they got some good stuff, and I'm sure they're going to keep trying. And it helps when the winds are blowing things up there. There was a couple of days there, well, it was really strong winds, right? There must have been some stuff blowing out of there that landed elsewhere. And as we've seen, we can, they have their whole solar panels covered in sample. They can just scoop that, brush that stuff off, and right. But you like to kind of do it every day, so you can make sure it's like, you can have the chemistry changing day by day. So, anyways, supposedly they're doing that, and so we're just going to await the results on that, and I'm sure they're going to be super excited to share, and we'll eagerly await that. So, thanks for that question.
Yep. Cody from Facebook asks, what's the significance of the water being present before? Does it indicate anything?
Well, so that's interesting. I mean, it indicates that that shaft that existed that was filled with rubble, the shaft that existed before 2018 that was feeding the lava lake, right? So USGS has described like a champagne glass analogy, where you have like a narrow stem and it comes up to a bowl at the top, right? And so the lava lake at the top of Halema'uma'u was the top of that, and that stem was feeding it from below. And after the whole thing collapsed down there, there was a big, column of rubble, essentially a big cone of rubble down in there. And so the idea might have been that if there was magma able to somehow still be in there, then it might be too hot for the water to come back into there. So it's pretty unusual to have the eruption, the magma withdraw deep enough, with the combined crater being deep enough that the water table could then fill in an area and be visible to people on the surface. And that's essentially was all it is. The bottom of the pit was below the level of the water table, and that's kind of why it was fascinating to see that. And of course, the historical context is there are Hawaiian stories of perhaps up to 4 different pits with lakes in them inside of Kīlauea caldera after the 1790 explosive eruption of the volcano. But that's just oral accounts and kind of shrouded in the telling of the stories and the storytelling traditions that are fascinating of Hawaii. So yeah. That's really it. Like when lava comes, let's say this eruption were to end whenever it ends, and let's say we have a giant pause. I'm not saying that's going to happen, but let's say that we had another, 5-year pause or something. The lava's going to be in there, and it's going to be hot. The water's going to try to start coming in from the sides, and now it's going to encounter that hot, cooling lava, cooling from the outside in. That's going to have that core of liquid that's going to stay liquid for decades, right? Unless something else collapses it or pushes it out, or something else crazy like that happens, which that's where it would happen. That's where the crazy stuff happens, is in that pit. So after many years, now that the ground is no longer that deep, we can't see where the water table would come up. We're probably not going to see ponds on Kīlauea until the next summit collapse, and so that might be, the last one took 230 years. Between, right, of the size were collapsed deep enough that we have evidence of water at the bottom of the pit from the groundwater. So it's like a historical curiosity and significance, really. But the fact that it was there, maybe is why we have an island. If you have that pond just sitting in there and the lava's pouring into it from above, and it has to have a chance to have some frothy interactions, that might be why that thing is a different kind of lava that's able to float on that lava surface that's rising. So, all right. Next, Dane.
Right. Does this eruption affect Mauna Loa, and in what way?
Well, that's a fascinating thing. I mean, it doesn't affect it in any kind of urgent way whatsoever, right? We can say that Mauna Loa seems like quite a down a little bit. We'll visit Mauna Loa in our next update, because we'll have another weekly update from USGS on that as well. But there's nothing happening on Mauna Loa apart from essentially quieter than normal. Still some activity happening, but what the way I imagine and have described these volcanoes in the past is they're not actually connected. Like their magma is not connected. It's like like Dana and I, we have different hearts and different circulation systems, right? But if we're trying to fit into the same telephone booth and we're leaning on each other, then we're leaning our weight shoulder to shoulder, one on the other. Or maybe people getting in a crowded elevator, if you prefer that analogy, something like that, right? So they can affect each other by pushing back and forth right? And Kīlauea kind of sits above and to the side of Mauna Loa, so Kīlauea is like on it, kind of slanted. So whatever Mauna Loa does, Kīlauea is pushing on it or getting pushed by it. So there has to be an interaction because they're touching, right? Kind of almost touching and leaning on each other. So they definitely affect each other in that way, but the actual magma doesn't affect. So what seems to be happening now is Mauna Loa is somehow feeling, that whatever Kīlauea is doing, Kilauea's relief of pressure at the summit. We've seen everything around Kīlauea kind of contracting, right, as lava is able to expel on the surface and essentially vent all that gas that's building at pressure. And once that happens, then Kīlauea is not pushing Mauna Loa quite as hard. So Mauna Loa gets a little elbow room. It's a little breathing room there, and maybe she can expand a little bit and fill at the same rate she was before, without so many earthquakes, without so much deformation, because you actually have room. Like even if it's just a matter of like how much pressure is holding a crack closed, right? Those things can matter. So that's an interesting thing to think about. So
last one that just came in. This one's sorry.
Go ahead.
Last question. This one for this round just came in. If it is like fingers, do you guys think that a vent might open up somewhere else inside the caldera when the vent is covered?
It could. It could if the pressure to come out of another vent is easier. So let's say that the crack that thing is in extends below all that rubble up the hill farther than we can see. If the lava level were to cover all the way and a crack's already there, it might just work its way through that same crack and come out farther up. That's possible. In that sense, the crack could kind of extend and it could do something like that because the pressure balance might shift a little bit. For it to go and find a different crack, that would have to be easier than actually coming out the crack that it's already found, even if it's coming up through denser lava. So one thing we've seen in the past, we've discussed in our previous updates, is that the lava could possibly drain back into the vent temporarily, and then the vent can pressurize and then restart, and then depressurize. The lava can then drain back in, and it can restart and pressurize and go back out. And we may actually be seeing something like that happening, but not at the surface right now. I think there might be something like that happening underground, somewhere where all these vents kind of connect, somewhere down in here. But that's a really hard thing to try to comprehend there. So, but we'll look at some of the evidence that suggests that. So, and let's say that once this eruption is over, the magma, as we expect it to, just starts swelling the summit once again. Then it may likely come out of a different crack during the next eruption, and it'll happen again and again and again. But quite often, these cracks are the ones that are called the ring faults, the ones that want to circle around a caldera, so that those ones that form the inner pit, and the one outside of that, and the one outside of that, and the one outside of that. Those are the easiest paths for the lava to come out. So that is probably going to be nearby where the one is right now, right, and not anywhere outside of the caldera. So all right. And yeah, so
next round, if anybody has any questions, throw them into chat on whatever platform you're watching, and we'll get them sorted out and put on.
All right. And so just kind of one more note here on this diagram for a viewer here. This tubed over terminology right in here that's on this diagram I have on the screen just means that a crust has formed over the surface of the lava, but the lava is still flowing liquid underneath it. Right. So it's essentially formed it's like encase itself in a little cave of rock, right? The rock on the outside is frozen. And I've described this in the past as, having a river in the wintertime, having ice in the banks that freezes on the edges and meets in the middle. Water keeps flowing underneath. And the difference is that you don't have a spring. Unless the volume increases, then that thing is going to stay inside of that tube. Which is interesting too, right? If that thing is tubed over, is it easier to drain there? I don't know. That's kind of weird. So, things that are fun to think about there. All right, so let's move on to the USGS Twitter here, and let me give it a reload so we can get the most recent thing shown for you guys here. And I might need to zoom it in so you guys can actually see what is going on here. All right, so they have the helicopter video we showed you guys earlier, and here's an interesting thing that they reported earlier today. Overnight, field crews observed sporadic Strombolian-type activity from the 2020 Western Vent, and they're describing this as minor explosive bursts of lava, right? And so this is kind of a technical term. Volcanoes can be more or less explosive, and the bigger the explosion, obviously, the more dangerous it is. And so Hawaiian is like the lowest on the scale. Strombolian is the next lowest on the scale. Not to say that Strombolian activity can't be dangerous. It's just minor volcanically. It's still enough to blast any living thing, like to somewhere they don't want to be. So what they're saying is that this thing is actually going off kind of like a firework, right? There's some Strombolian activity typically signifies to a geologist that the gas bubbles are starting to collect and separate from the lava, right? That there's gas bubbles coming up independently of the lava as well as in the lava. And so the gas bubble is basically coming up, and the gas bubble, whatever size it happens to be, has to fit through whatever hole it is. So it may end up being long and narrow, and it comes out as a pop, 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 pop. And each one is putting out like a burst of lava that's, like a hacking cough almost, right? Just spattering that lava out of there. And that's landing around and making that cone that's visible in this image on the right over here. Right, so that's really interesting. Normally, for the gas bubbles to be able to nucleate and coalesce into those bigger sizes, that actually form that kind of character of activity, requires denser lava. Now we have denser lava right here. It's draining back in, right? It's draining back in to this northern vent after being fed in from this western vent. So it's quite possible there that there's some interaction of this denser, degassed, cooler lava mixing with the hotter, fresher stuff down there, and that the combined result is still able to is a little bit thicker than before, and is preventing the gas bubbles from coming out in a continuous stream, which would be a lava fountain, and is now causing interruptions in them. So you see like more of one than another than another. You might see periods where you see like a whole bunch for a few hours. Then it might pause as it's recharging the gas bubbles enough to move back through that more viscous lava, and then you might have a whole series again coming up and through, and it might do it again. So that's a kind of activity that's almost like having a rejuvenation of a lava fountain, but it's kind of what you see underground. And in the meantime, this thing over here is encased itself in lava, so lava is actually pouring out the bottom right over here. And you're kind of looking at the effect of the chimney being like, how much is it spattering or coughing, or is it fountaining, or putting out this more Strombolian activity. And so they actually mention their PPE and safety gear, because sometimes these things can be like big blasts, and lava can shoot out to possibly where they might be standing. You don't want something like that that's shot with that much velocity, and that much height to go landing on you, could be really hurt. So that's why they are preparing themselves in that way. And so other than that, pretty standard, right? Similar things that we've been talking about before, but that's something I wanted to point out. And if we look at the deformation data, let me give it a refresh here to see what has changed since the plot earlier, right? We're looking here at this 2-day plot, right? So we have over here is midnight on the 29th, and this is midnight on the 30th today, right? So you can kind of see that the volcano had been deflating. I have to go back a little bit more than that, but it actually had been reinflating when it started deflating again, and reinflating, and it's deflating again, and reinflating, kind of stabilizing over here, right? So there's this kind of up and down pattern to the pressure now, like it's able to build pressure and relieve pressure, and build pressure and relieve pressure, right? So we'll see if that continues and how long that goes on. But that's the kind of thing that may be a result of that denser magma. The overall pattern of increase, though, like that's something that may be what lends people to believe that this might go on for longer or not, because you really have to want to see eruption doing this to believe it's going to be ending anytime soon. So, but it's interesting to see like what effect there might be. So possibly they drain back at this denser lava if it's able to pressurize a thing and allow it to kind of repressurize it for us, to relieve it and pressurize and relieve it, and may actually extend the eruption through some mechanism like that. So that'll be another fascinating thing to watch as well. All right, so we'll kind of scroll down. We can see the last week, and so we were zoomed in just to this area right over here, right? And we're looking at these changes that were essentially between 1 and 1 minus 1 microradian on our axis over here. And so we're looking at the blue line, that's Wikuhuna. The green line is Pu'o'o, which is offline, so you don't see that signal past 26 over here. So we're just going to ignore that. You can kind of see that our long-term pattern, when we had the northern vent active, was of deflation until that turnaround time when the western vent took over, and then we're able to kind of pressurize, and it's very slight release, and pressurize, and very slight release, and little release, and pressurize, and little release. And so overall, the trend you can see since the 26th is still definitely up, right? And that's what I'm talking about as far as, you know, that's if we're building pressure, then how can we end eruption? You know, kind of that might be what kind of extends it out. Would be something like that. And so looking back to the last month, you know, it's interesting. We're only a couple of days away from the 1 month anniversary of the intrusion that started this whole thing off. This is a signal that's going to scroll off of our graph here, you know, by our next update to you guys, most likely. And just to kind of point out one last time here, we go from maybe -8 to somewhere in order of plus 12 or something like that. So it's something like a 20 microradian. Right, much bigger than the previous changes we've seen. And then overall, in total, since the eruption began, we've dropped down during that first phase to, you know, not quite -30, maybe -29, and, you know, this might be somewhere in a range of 16, right? So 16 plus 29, that's 45. So something in the order of 45 microradians we've come down, right, since the eruption began. And so while we have been repressurizing it, we've only repressurized at a total of, let's scroll to this upper one right here, from -3 to +1, 4 microradians. Significant, but that 4 doesn't compare to the 45 we already lost, right? So that's why the long-term trend, since this eruption actually started, is still a downward trend. So that's kind of, you know, more about how is it going to tail off here at the end, which has kind of been the focus of our last few updates, of trying to decipher that as the signals come in from different parts of the volcano right here. And so that is the one way to look at it, and we'll look at more tilt here in a second, but I wanted to kind of jump to a couple of our seismic stations we have on the summit of Kīlauea. So this one is Byron's Ledge, BYL. If you look on a USGS monitoring map, this one seems to show a signal like a little bit earlier. It seems to be maybe somewhat closer to the source, or some more sensitive to the source somehow. So this one is showing a signal coming in maybe around 4 o'clock, 4 a.m., something that it kind of begins. You can kind of see it gets a really strong bend right at 6 a.m., right in there. And that's much heavier blue lines in this period right here than clearly in this period over here. Maybe a little bit stronger right in there, but fairly minor. And kind of, we got to scroll back in the previous day here, and you actually had another stronger band, you know, back on the 28th. Right, the 29th goes by from midnight to 29th. Midnight and the 30th, without a whole lot happening as far as tremor increase on summit of the volcano. Whereas since then, you can kind of see, let me give this thing a refresh as well. And I'll have to scroll down here for you guys. Come back to our, you can kind of get a view through here. Oh, it's going to load. That one did not want to load for me anymore. All right. So, but we'll scroll down to this other station, HAT, and you can kind of see that it has some bands on the 29th. So this might be something that's closer to the vent. So this is not clear if this is actually jetting from the vent there. So, you know, we might have gas coming from build up more shallow under the lake, and maybe gas coming from a little farther away from the magma chamber. It might be something that these two stations are sensitive to in different ways. It'd be fascinating to hear more about that from the geologists working at the USGS. So quiet period essentially, you know, yesterday afternoon, and this station here, you know, may be actually seeing more of the vents. So let me see if I can zoom in. You kind of see this little speckled, like, you know, that little signal there, and then this little signal here. These may actually be this little explosive blast of strombolian kind of activity. You kind of look at this part of the seismograph, you see lots of these things separated by a few minutes, like, you know, a little burst and a little burst and a little burst and a little burst and a little burst, right? Before you have this more continuous activity further down here, right? So that's really interesting to see that, you know, stronger activity down here. You kind of see you have that first pulse somewhere around 6 a.m. You have this signal right here, but then it really comes in more so around 8, like in 8 to 10, and kind of dying off more slowly, but something happening, you know, all the way till it looks like almost 5 o'clock, and then since then, in the last couple hours, it's quieted down again. Right, so it's interesting because if we go back to our tilt drop here, and let's zoom into the 2-day plot here, and just look at what happened at 6 a.m. today. 6 a.m. today is when we have this big drop and a tilt right here. We have one big drop kind of right around 6 a.m., just before, actually. And we have another drop, not quite as big, over here, right? So maybe this is the, you know, we see the signs of that first gas bubble starts moving towards the surface right here, right? And when the thing starts quaking, tremoring, vibrating more as the gas bubble was moving its way up and through. And it could be that it was actually moving, you know, building pressure somewhere in a range up to here. Maybe it was being felt at another station a little sooner. And then another drop right in here, and that likewise could have been corresponding to that, you know, there's a little bit of a pause right there as far as like the tilt dropping. And then it picks back up again, and that's when we see that second band of tremor really come in, right in here. Right, so it's interesting how those things line up, right? And that went on until, right before 5 o'clock. So stepping back over here, right before 5 o'clock, and it actually was repressurizing by that point in time again. All right, so interesting thing. These are small scale variations, right, of our whole 45. Now we're looking at between 0 and 0.2 for each of these lines over here, right? So we're kind of micro-analyzing the micro signal here, right, to see try to figure out what's going on. So all right, let's go over here. And I just want to kind of point out, this is a little bit of teaser for later. I'll show this again later. But this is going back to the lava lake of 2016 at Halema'uma'u summit, and a study that's put out, and you can clearly see that there's times of elevated tremor corresponding to spattering, moderate tremor, intense spattering, and high tremor. No spattering, instead of having a gas piston, that means the gas kind of rising the whole lava lake up as a whole without bursting out. Then you have tremor stagnation, right? So this is not anything new I'm talking about here. This has all been established before. All right, so what do our other tilts look like? Right, so looking at our 1 month tilt, let me also refresh this so we can have a more current view. And so that's at Wakahuna Station, the summit we just saw over here. You can kind of see that pattern of that big drop down. There's a 45 down, and then here's our 4 back up. And you know, this is what we're seeing come back up. You can see a little bit of wiggles happening right in this period right through here. So that's what we just looked at. Let's look at Sand Hill. Sand Hill, you know, before this, you know, while it's still pressurizing, building up, we can see this cyclic variation. So we know there's another cyclic signal being put on there, whether it's the daily temperature or a miscalibration for the tides or that kind of thing. You know, those are kind of things that the instrument's sensitive to. We don't know exactly what that is, but that's probably preserved here to some degree as well. So it's harder to tell what's going on as far as the cyclicity here because we know what's happening before, right? In comparison, you look at what's happening at Wakahuna before, and we don't see that, right? We do see our deflation-inflation cycles, which interestingly did not tell us much of anything as far as how likely we were to have an eruption or not in the end. But they were there, showing us that the upper chamber was still active. And in comparison down here, we have all those wiggles, right? So that's something we pay attention to. So, but the Sand Hill also rising, right? And one thing we were pointing out in the last couple updates is that at Kīlauea, you did not see that signal. They actually saw at the switchover, we still saw deflation going on. And however, that did change. That just changed recently, just within the last day and a half, perhaps. And it does look stable, like it's actually flat now, maybe possibly resuming its other trend. But it's interesting how it had a little hiccup going on there. It actually did come back up at Kīlauea as well. It's just a little noticeable thing, right? Very, very, very small change, right, on our scale here. So We have a little bit of signal from the summer camp, and we can tell that summer camp appears to be rising as well, right? Kind of a trend going up, at least right over there, very, very slightly. Our escape road station, we're saying that this signal we see here is consistent with tipping north as the caldera sags as eruption begins, right? Eruption beginning somewhere in the area right here. So this station being an upper east rift zone within range of the edges of the Great Caldera is still feeling the caldera deflating and it's tipping to the north. And that tipping seems to be stabilizing, right? It's not quite done, but it's still stabilizing from farther away. And we don't really see anything new from Pu'o'o, although at Pu'o'o we did see that it was also dropping in tilt, right? Showing kind of depressurization as a result of magma going back into the summit from the rift zone, which is the opposite pattern as we saw from 2018. Right, so that means a lot less risk for anyone down the lower east rift zone as well. So okay, we're gonna switch to some questions. I'm gonna first pull up some USGS ones that are in there, and the question: how far down is that lake still liquid lava? And probably most of the way down. It took decades for the lava lake in Kīlauea to solidify, although the lava around the edges hardened sooner. These lakes cool from the outside in. So what's gonna happen is we're gonna have our pit down there, and we're just going to cool that edge first, and it's going to come a little bit smaller that way, and then a little bit smaller that way, and a little bit smaller that way, right? But it's probably not going to go past that first little rind until the lava stops pouring in it. Really, that's kind of when a clock really starts. You might be having like a little bit of rind forming at the very edge right there, but it's pretty insignificant compared to the size of the whole lake and its breadth and depth, right? So that's something that I've shown a cross section of, and a couple updates ago we talked about Kīlauea. I'm not sure which one it was anymore now. They're running together. We've been doing a lot of these. Next question: is the island rising? I thought we'd see the island shrink in size a lot more by now with a lava lake growing so fast. So here the USGS comes out and says, Dane, the island isn't really an island at all. It's a raft. It's rising with the lake. So you can see that they clearly have that same discussion as we have had behind closed doors ourselves. Gonna jump in here.
It's just funny because like we've been talking about that one. We were also talking internally about the gas levels being similar to the 2017 pre-collapse levels that we saw in the continuous lava lake there. So it's just like a lot of the conversations end up being very similar. Behind closed door, we find out later.
Right. So let me just pull up one more question, and then I'll have Dane direct them to me here. But so here, Kate Laxton replying to USGS tweet, asking how wide is it, right? And so she just wants to know, is it going to be officially the largest lava lake in the world for now? Because Nyiragongo in Africa might have been the previous holder. And so they say, citing a thermal map on December 28th, their estimates of 770 meters by 490 meters. Right, compared to 230 meters by 220 meters at Nyiragongo. So as of current, it appears that the Halema'uma'u lava lake is the largest lava lake in the world while it lasts. Right, Nyiragongo is kind of a long term. It's probably going to be there still whenever this eruption is over. Right, or possibly depending, it could be a race to see who can last longer. Who knows? All right, so. Dan, you want to throw me some other questions before we go through some of the imagery from USGS here?
Sure. So, Patty from Facebook asks, the decreased earthquakes lately, is that a signal that things are slowing down?
Not necessarily. It just means that there's an open pathway. So it means it's slowing down as far. The earthquakes really tell us about the eruption beginning and about pressure building up. So if we saw earthquakes actually building back up, we might say, okay, it's pressurizing, even though it's putting out lava, right? And then that would be a concern, and we would have to think about how to relieve that pressure. But we're not seeing that, right? We're seeing the lack of earthquakes, and that doesn't tell us much of anything at that point. Besides, it's open and it can get out, basically.
Right. People might remember in 2018, the earthquakes came in May, right? And they stayed pretty much through May, but by June, there were hardly any earthquakes in the lower east rift zone, right? A couple here and there, but more average levels than what the eruption, the thousands and thousands a day that it was doing in May. And the same was true through July and into August. And then it kind of tapered out without earthquakes.
Right. That's, yeah, a great point. Great analogy as well.
Yep. So, Joe from Facebook asked, what's the difference in weight between molten lava and dried lava?
Well, it's all about the how much gas is trapped in it. That's really more important than anything else, right? So like any lava rock has a bunch of gas bubbles trapped inside of the lava rock. If you have a magma and it cools all the way underground, it forms a solid intrusive rock, right? Something like a granite. In Hawaii, we don't have granites because our magma is a different chemistry. We have what we call gabbro, when it's just made of giant crystals, or all like a granite, all interlocking, right, and big. That essentially, show like no gas space whatsoever. So when when a magma makes it to the surface, it becomes lava, and at that point, it's coming up because of some gas that's being nucleating within it and causing it to be buoyant and rise up. And so whenever it actually cools, it's going to trap some of that gas. And so, anyone who's visited Hawaii and the lava flows of Kīlauea knows that sometimes you can get like really big bubbles, and sometimes really delicate ones that are really super thin. Sometimes you can get like, ones that you step on and you fall away into. And sometimes, you just look at the rock and the rock just kind of feels spongy to walk on because you crunch, there's so much give and cracks and throughout the whole thing. So it's more of a matter of like, how much bubbles do you have compared to how much not bubbles, how much lava, because once the thing actually cools, that ends up being what the change in the weight mostly is, and density to be exact, right? Really is. And so that same comparison goes for the lava that has more gas in it and lava's got less gas in it, right? So the difference might be, I don't know, on the order of like 5% or something like that. It really depends on how much gas, right? I'm trying to judge for this particular eruption. For ones like when you had just so much, gobs of gas coming out, like Fissure 8, the numbers coming out of Fissure 8 were just ridiculous. When you have that kind of thing going on, then then your volume is kind of increasing as well because it's just so frothy. So then it's kind of hard to, it's almost more gas than there is rock, right? That's why that stuff can blow in a wind so far. So I didn't exactly answer your question, but that's the best I can do right there.
All right. So Buckskin from YouTube asks, if the fountains continue to erupt over the next 30 days, what is to be expected? So assuming, continuous activity. Let's just put that out there first.
Right. So let's say that the input feeder from below is continuous, right? And what's going to happen is the lake's going to fill until it actually perhaps gets as high as that second vent, right? And at that point, it may actually have to readjust. It may be able to, the eruption may actually stop more so at the surface rather than what we're seeing below it, because even though we're describing these changes in the seismicity, the tremor, and changes in the tilt, lava has been pouring out that bottom plunge pool of that western fissure the entire time continuously. It may be slightly slower and slightly more dense and slightly more gassy and slightly more frothy at other times, but it's been pouring in continuously the entire time. So that might stop, and then you might have a start-stop scenario, right? And then
one thing is, at the current rates that it's been rising in that level, even if you're generous and say like, 3 feet a day, it's going to increase in the level, which is going to be generous. You're still short.
It's not going to get there in 30 days. Yeah.
Not going to get there in 30 days.
Yeah, it's a good point. I kind of extrapolated beyond that, right? That'd probably take months for that to happen. But that's yeah.
All right, so one more here. Looking at the seismic charts that we were looking at earlier, they're wondering how long the duration of one line is, and just kind of walk through that seismic chart a little bit and kind of just describe what people are seeing here a little bit.
Yeah. Okay. So I could do a little better there. So this is a station that if let me zoom in so I can show you some of these details in here, right? So the top of this plot, like on the left side here, is giving us a date 12/28 2100, 2215, 2330. So it starts at these times on the left and goes across to the right, and one line traced left to right is 15 minutes. You go all the way over here, and you have, the corresponding. This may actually be an universal Greenwich time on the side, and this may be in Hawaiian local time on the side over here. So I often look at this left side when I'm looking at the times here. It can be confusing if you look at the wrong side, yeah. So yeah, and then basically you have 15 minutes going down. So that's, that would be 9 o'clock, 9:15, 9:30, 10 o'clock, 10:15, et cetera, et cetera, et cetera. And so I've pulled up here, maybe I could show you guys. Let me go to, where can I find it? No. Well, so if you go to the USGS site and go to the monitoring page and you click on their seismic stations and you pull these up, you get different options of which ones to open, right? I've pulled up the 48-hour one. So I have, from the evening of the 28th, I have the whole 29th, I have all the way to the evening of the 30th over here, right? And here's our label, time Hawaiian Standard Time at the bottom. And here at the very bottom of our plot, minutes, it gives us a graph, 1, 10, 12, all the way to 15 here. 15 minutes on this side, and time and UTC on the right over here. All right, so this is just one way to look at it, is actually the 48-hour plot. They also have 24-hour plots. I can show you guys a 24-hour plot. Oh, I'll go back in here. And that's a 24-hour plot. They have 12-hour plots and 6-hour plots as well. So yeah, that's basically it there. All right, so I think that
kind of does it for now.
All right. Well,
we do have, you want to take that one. Do you have a hypothesis for how the rafted island formed?
Yeah, that's what we were talking about a little earlier, having a presence of water there, and kind of imagining that you might have to have some kind of trapped gas bubbles in there somehow, some interaction of the lava and the water interacting. The explosiveness, the kind of bubbles that form, you have enough of that stuff getting trapped, the lava's coming in fast enough it buries it somehow, and you actually get some gas trapped in there. Then you can have a kind of frothy, gas-rich lava chunk that then when the lava comes in, it actually ends up floating on the lava, and it's being eroded and melted underneath, but at a slower enough rate that we don't actually see it. In only 10 days it's been of eruption so far, right? So there are examples if you go back to, I want to say that Lauren Thurston in 1894 described a collapse of the pit, and he described chunks of the crater walls actually collapsing into the lava lake, and how lots of the smaller pieces would plunge through the surface of the lake, like kind of breaking that surface tension and just sinking all the way. But that one big one plunged in and wasn't able to break enough of that and ended up bobbing. And that became one of the islands. It was from a chunk falling in from the walls. There have also been reports of there being cinder cones within the pit of Halema'uma'u, right? Like imagine we have, the next eruption happens now on top of like what becomes a hardened lava floor, and you form a little cinder cone right there. And then you have another fissure later that comes in and pours into that. It could actually pick up that cinder cone and lift it up, and they could make a little island out of the cinder cone. So that's another possibility of what could happen as well. You might have, if you were to be able to watch and document this volcano long enough, you might see examples of all different kinds of things like that happening. So in our case, I don't think anything fell in there besides the actual liquid lava, and it fell into that pond of water, right? And I think it was that interaction, kind of freezing the lava with a lot of gas or steam, essentially allowing more space in there, that even if that particular lava was kind of cracked around, if the other lava coming over it was able to kind of then encase it over and over and over and somehow trap all that behind so many layers of lava that you essentially have a float, then that could essentially provide the mechanism for that thing rising, floating in the lava. All right, so we are going to get to our historical section a little bit later, where we're going to discuss the observations of that as it happened before. So, all right, let's see. I wanted to next make sure we cover the photo and video chronology pages on the USGS website here. And so I've showed you guys a video already, but this one here was yesterday, 5:30 a.m. with the moon. A lot of moon pictures coming through on Hawaii Tracker. If you guys want to see a lot of the local photography and people sharing their experiences with each other, visiting Hawaii Volcano National Park. You can kind of see here, we still have that plunge pool, that western vent. A lot of gas obscuring what's actually going on here, but you can kind of see there seems to be like a little bit of open pathway with just a little bit of crusting over happening at this point. But you can kind of see that the delta is building up already. It's kind of all this material is building to the sides over here around the vent. All right, and so here we have scientists monitoring. You can see this scientist is standing on the old crater rim drive right here, the double yellow center line. There's the edge of the collapsed crater right there, and then she's looking over this edge with this appears to be maybe a video camera, and looking at that vent down there. Here, the USGS is showing that they actually have landed on a down drop block over on that eastern side of that kind of east and over the pits down over here, kind of that lower ledge. This is like the upper ledge of it, like that 900-meter part of it, and then an 800-meter below, lower down in there. And the lava lake through the ground is down in there somewhere like that, you know, within the pit. That's like that. So they're putting a GPS station. That's what this thing is over here, with a solar panel and some electronics, data loggers and transmitters and all that kind of the brains of the thing to relay the signal back so they don't have to come back here all the time. And see how this piece of ground right here, very close to the vent, how it's moving. And it's maybe one of the more sensitive spots to tell what's going on. And so this would be an interesting signal. This is a signal that they probably have running behind closed doors. I have not seen or been able to check if this is online yet, Dane. Maybe you can check for us on that at some point and report if it is. But anyways, what's that?
Yeah, I'll look and see if I can see something.
All right, great. And so they once again, they were reaffirming in their quote here that they're just talking about contraction of the upper portion of the east rift zone between the summit and Pu'u'u. Right, so everything downrift of that is stable and no motion. So that's kind of what they're saying here. So they interpret this as indicating magma from the contracting portion of the east rift zone is flowing back to the summit reservoirs where the eruption is occurring. But the patterns of the formation could also be influenced by the decrease in the amount of lava erupted from the western fissure and the draining of the lava into the now submerged northern fissure vent. The signal is small, and preliminary modeling shows it to be a small amount of magma returning to the summit. Right, so, and then go ahead and mention that this is the opposite of 2018 right there, and no new hazards expected. Right, so that's interesting to see there as well. They're actually, as before, mobilizing to deploy more instrumentation to get better data during the eruption, so they can make better anticipate what's happening and go from there, right? So this is a big part of it as well. And at some point in the future, when we have more time, this is also down. We can report like all the different things that happened in 2018, how many instruments had to move around and all of that as well. So I'm not sure exactly what station this would be over here, but this is kind of this may not make it online for us to actually see, and we'll have to wait for the reports to actually see what's going on there.
Yeah, I'm not seeing that one. Remember in like 2018, they had some new ones that they put out, but they weren't listed publicly, but they were still online. You just had to be able to find them. So if it is online, I think it's like that right now, if it is.
Right, so yeah, so we, like the rest of you, will just wait for them to release the data when they are able to, and we'll go with what is online at this point already. Yep. So all right. Kind of scrolling down, we're still going through yesterday's image updates here. You can kind of see kind of similar, all the gas within the western vent. There is that main island. The other 10 are over here, right? You can kind of see a little bit of this kind of arcuate shape going both directions. It's almost like what you see on the surface of a Pahoehoe channel, right? The skin forming on the surface and then kind of crumpling up, rolling over itself as the lava underneath is able to move faster than it, and the skin kind of gets rolled up into these kind of bumpy plates, rough, dark textured plates right in here. And this kind of lighter colored lava, that's the hotter stuff that's breaking the dark plates apart. So over here in the back, you can kind of see between these islands, there's an interesting pattern of these kind of darker plates and then lighter plates in between them and darker plates. And so this may be an area where we might have that downwelling happening, where everything's able to plunge down and in order to backflow into the hole over here, and then possibly maybe it's going underneath this way and flowing back down that hole over here that's buried under here and over here as well. Who knows? But there could be that kind of dynamic happening there. All right, and another rainbow picture. There's been a lot of steam from this eruption. And the top of the volcano is at 4,000 feet, right at the crest of the trade winds, and so quite often as an area have mist, some rain, and so quite a lot of rainbows in recent days. It's been fascinating to watch from the USGS right there. Double yellow line dropping off into nothing here from the perspective of the camera. All right, so we're gonna catch up to today, and so overnight, this is the view, and kind of a similar thing here. Western fissure, mostly encased in solid lava, but still flowing underneath and plunging into the pit. There is that big island, but even without that, we have some pretty big pieces of plates. These plates are pretty big here, right? It's interesting to see how you can form those when a lava surface isn't moving as fast. You can form these bigger chunks. And here, kind of zooming in to that Strombolian activity, we saw a little bit better picture on a Twitter account there. So keeping going here. A little bit better light for this view. You can kind of see a little bit of the different textures of the old pieces of crust, especially much darker on this side over here, right? So it's almost like they're collecting over here. So the surface lava isn't coming up here as much, and if it is, maybe it's coming from below. So it seems like it's diving under right there, and possibly there. Right? Maybe this is getting over here, so it stagnates the flow, and this area is more stagnant than the area closer to the vent, right? And maybe that's why these islands are all happy to just stay there without moving quite so much. Although we'll examine that here shortly as well when we look a little bit more at the thermal image. So okay, this summit view, you can kind of see what looks like a little bit fresher surface here coming out, right? With these kind of more silvery, more shimmery ribbons compared to the darker crust over here. So this might have been like a switch over time. We're having more gassy lava plunging into the pool, perhaps, during one of these periods, right? So, right, it kind of, that's based on that seismic terminal we were looking at earlier. And it's interesting, now we've come to the end of this second photo here. It's interesting to try to go back and examine a little bit what's happening with the thermal, right? So this is I'm kind of going to go through a little bit slowly here, so you guys can kind of see how this western vent has been behaving. All right, so I'll just kind of play it through so you can kind of watch. You can see the island is spinning here in the middle. Right, you can kind of see that flow that goes both this way here. I'm going to change my color. See flow that goes both this way and this way, right? Here's that big crust, big chunk of crust. Right. One thing to notice is this margin right here on this black ledge. Right. So you can see that there's times when this thing is kind of lapping up and over, kind of in pulses. Right. So let me try to play it for you guys again. Let me pull it back if I can. All right. So I went moving over. Splash over, another one, another one, another one, another one. That's like a longer lasting high pulse, but then pulsing over and over again. So it may be that you have, at these times of more gas emission, this thing may be possibly lapping up and over more on the edge here. Maybe it's more, maybe that's showing, if the more gas is coming through and venting out the top of that vent, it's possibly mixing with the magma also, and the lava that's pouring into this plunge pool down in here may be frothier as well. And so that means it takes more volume, and that could kind of increase the depth of the lake and cause it to slosh over like that, right? Now, not only that, it must be actually filling the thing, because every time you slosh lava over this level, it's not like water. It doesn't just soak into the ground. It actually deposits another layer of rock on top of this. And so the actual height of the black ledge becomes taller. So the fact that it keeps doing this does indicate this lava level is coming up, as we saw in the graph as well, right? It's able to actually keep lapping up and over and up and over and up and over. We see how it's doing that a little bit in that kind of cyclic fashion, right? Almost like in a pulse and another pulse and another pulse. Whatever term you choose to use, you know, it seems to have some kind of start, like a little bit more, a little bit less, a little bit more, a little bit less. Right, so let me go back here to the where we were and just play it through one more time and kind of, you know, just manually advance it. With these last few hours, you don't really see a huge change in the circulation or anything like that of this lava level, right? You know, what you do see is kind of like back in this more stagnant area over here, you see these kind of older crusts trying to persist, and then lava kind of wells up, and lava wells up through them, So another area to keep your eye on is lava kind of wells up and wells up and wells up through there, right? Back and forth a little bit there, right? You can see the wiggling of those islands. Right, so they seem to be staying, you know, wiggling, but kind of staying in that general area right over there. All right. So moving on. Let's see if there's any more maps put up by the USGS. If not, I can show you the one that was put out yesterday, kind of the newest compilation of thermal imagery and the aerial imagery. So you can see the darker spots in here. I can zoom in even more. Well, that's as much as I can zoom in. So there's our 3-acre island in the middle. All this kind of bluish stuff is the actual lava, right? The darker the blue, the cooler it is. And so if it's actually red, it's the hottest stuff right in there. White is also hot. And here's those big pieces of that crust we see in that thermal image right through there, right? And the darker ones are the islands that have deeper roots, right? So the down-drop block is this area over here. For those of you guys who are wondering, I've mentioned it before. Right, this is the inner pit of Halema'uma'u right in there. But there's like an upper crater lip that's more over here, drawn before. And then there's that kind of edge of the down-drop block right over there that kind of comes around all the way like that. Right? And so that seismic station was being installed somewhere in the area, I would imagine, over here or something like that. Right? It's interesting, I don't know if you guys noticed in that image. Right, the plant life that still persists growing over here in that down-drop block. Right, all those plants that went for a ride during a crater collapse, and there's stuff still growing in there after all that, and lava still right there next door. So Hawaii is a fascinating place. Lots of plants and animals adapted to the activity. That's a story for a whole different day, though. All right, so we want to make sure we cover the impact of the gas as well. So let's load and go through our typical air lineup here. And so here's our statewide Department of Health monitors showing green, although we have measurements in all the islands, you know, showing 30, 43 measurements over there, but everything's in the green today. Particulates, everything's green. We look at SO2, everything is still green. So we go to purple air, and let's reload purple air. So it doesn't like to be in a tab. And our purple air is showing still concerning levels down here in South Kona. Kīlauea, Kona town itself is kind of got some yellow measurements, but fortunately the areas north, Waimea and North Hawaii are in the green, right, as well as the volcano itself. A little bit borderline and ocean view right over here as well. I wonder what's going on with this one measurement over here. There's someone running their meter next to a exhaust fan or something. All right, so our most recent VOG model, right, does include the reduced output, right? So if you guys will recall, our SO2 emissions have dropped dramatically, right? So we think our effusion rate, amount of lava come out at any point in time, is related to the gas rate, and there's kind of a curve it's kind of taking, but definitely even with the winds, you know, blowing it right at you, there's a lot less coming out now than was coming out a week ago, right? That's clear. So with those numbers in the VOG model, You kind of see it's still pretty bad in the Pahala Ocean View area, right, as far as direct impacts, but there's also quite a lot of stuff lingering that's not really seen here in this model, right? So statewide, this thing is being pulled offshore away from the other islands as well. Right, so looking at the monitors at the national park, everything is in the green. We did have at the campground one high alert earlier this evening. There was a station trailhead earlier this morning, one quick spike. So, it could be that if you guys are visiting the park in the main area, that you will have occasional whiff of the fog, as the wind blows through. So something to be careful of if you have any respiratory concerns. So over in Kahuku, this is over by Ocean View as well, showing more signals in SO2. Not really anything coming through in the particulates on a park reading right there. And we'll reload our windy model here and show you guys what is happening with our plume. And it looks like our flow has kind of come back and over this way. So we've cut off that flow of fog over to the mainland, and now it seems to be more resuming its rather pattern over here. Locally, you can see why it's Kona, South Kona, and South Hawaii, and not so much in the other islands, although something possibly measurable coming back up through here. Perhaps in the upper levels of the atmosphere where, we don't have our on-the-ground monitors as well. Okay, so I think there's one last thing we want to go through here, and that's the earthquakes. And looking at the earthquakes across the island here, you can zoom out. We have one kind of still aftershock of an event last month on Mauna Loa. We've had a few events here in the flank of, Mauna Kea of Mauna Loa. Here we have a flank of Mauna Loa. And under Pahala, our kind of hotspot feeder source zone is still rumbling down there. We did have one earthquake at the summit, coming up as a 0.7, so really nothing to speak of there. And one kind of south of Pu'u'u, 1.2 right in there. So really not much going on. I'm just showing you guys, this is just the last day, right? The last 24 hours here, so not a whole lot going on there. And with that, I'm going to switch to the story or the history of the lava lakes. Although we could take some questions in between here, and if there are some quick ones to take here, Dane.
Yeah, they're not exactly what you're talking about, but
okay.
Or this one was actually, it was about the when you're showing the time lapse from the the time lapse from the thermal camera, right, and the lapping of the lava.
Mm-hmm.
Question was about is there a different signature chemically in the lava each lap that it does up?
That would be possible if the chemistry of the lava is changing between each pulse, right? So that's something that's fascinating to think about. There's a study done at Kīlauea where they actually could tell the glaze layer from each successive fountaining event, right, as the lava level rose and fell around. They also had pieces of their cinder cone fell into their lava lake and are now seen as bumps in the floor of Kīlauea crater. And they essentially were like, I like to call them like lava bergs, right? They're kind of floating there with like a deeper root as well. And I'm not sure if those things ever moved or not. They might have actually stayed attached to that crater wall because there were really big chunks right in there that fell in. But there they could see different layers because they did see an evolution fountain to fountain. But they actually had, in that case, sometimes a day between each lap, right? So if it's like one and another an hour later and an hour later, then probably not. You might see all those as kind of one unit, because the chemistry is changing, but I'm not sure we have a resolution to see it changing on that fine a scale. Hopefully someday, maybe that's happening, but I don't know that detail, right? You might see something more over the course of time, right, where the lava coming out earlier in eruption compared to what's coming out now. The lava coming out now might actually show a combination, a signature of it being mixed with of the hotter lava and the older the lava that's drained back in, mixed together. Whereas the early stuff wouldn't have shown any of that. That's more of what I would expect to see, that kind of overall trend. And within that trend, you might see like small scale variations with each lava lap if you could get the resolution with your instrumentation.
Yeah, I think that's going to do it for questions for right now. We'll get some more come in for you for the end of this one.
All right, so we're gonna step back and we're gonna go back to the summer of 1911 when this gentleman over here, Frank Perret, who is famous among volcanologists for several different things that he did, was the first person deployed by Jagger. He actually arrived before Jagger to examine Halema'uma'u lava lake, set up the first observatory, wrote the first articles about what's happening. This picture right here is actually him showing the lava sample he took, that they actually managed to sling a cable across the lava lake and dip a weight into it and pull out a chunk of lava, right? Yeah, it might seem like, oh yeah, no big deal, okay, whatever. Well, it's not as easy as it sounds when the lava lake is the size that it is, and you have to like walk around and all the fumes and all that, and what was available to them in 1910, right? As far as getting it over here and using it and all the manpower as well. So they actually try to get a second sample, believe it or not, but because it, the lake was bubbling more, perhaps where they dipped it in, that thing melted their wires and everything fell in. They weren't able. This is the only one they were able to get. So it was actually a pretty impressive feat when all is said and done. So it has been featured by USGS before. There's a volcano watch going back June 2nd, 2011. If you guys want to know more about Frank Perret, you guys can go there. I'm not gonna go into it too much, apart from to say that Perret and Thomas Jagger met on Vesuvius in Italy, right? And that was a place that Perret had gone to study the volcano. And so he actually had experience watching volcanoes. He brought from Vesuvius, and he'd also visited other volcanoes in Italy, and then he brought that experience to Hawaii, and he was the kind that took the first observations here. So we're going to go back and look at some of the photographs that he put out, right? Starting with this one, right? This is the Halema'uma'u lava lake with a floating island, right? Back in 1911, they're calling it a floating island. It's an island. Well, it's a floating island in this case. And you can kind of see here, there is the edge of the lava lake. Right in there, it's kind of within another pit. You can't see the upper crater right there, but it's in another pit also, right? And there's an island, and there's lava flowing all around it right there. And so it's kind of hard to see on its own, but that's kind of the setup right there. And on this island, they talk about how there was lava that was draining back into this little isthmus, this little neck between this big chunk of it and this big chunk of it. Right, and so Perret called these lava grottos, right? Because as the lava is going back into these low areas, the lava is kind of splashing up, and as it splashes up, it collects and builds up on that upper rim, right? Whether this is an island or whether it's the edge of the lava lake. Quite often, it's the edge of the lava lake where this is happening when you don't have islands. We have that same pattern of stuff happening in 2018. There's videos from USGS. We can go back someday and look at those, but that exact same thing is happening. Lava is essentially going down into that area right there. So it's interesting that this island, when Perret arrived here in 1911, was of this size and height and all that, but is also showing this feature, right? And to kind of advance a little more, here's kind of zoomed in what it kind of looked like. He's talked about there was a void, and lava would cascade down into this void for hours at a time from both sides of this isthmus. And so somehow there was a void space being filled in there, like whether it was filled with some gas before that, or he presumed that this thing was actually being molten from below, right? That's something that, because this thing was in the lava lake for so long, and it happened to be parked over this rising bubble of gas. That bubble of gas was eroding it from below, and was able to kind of build up areas where once it was able to vent, essentially opened a path to the surface, the lava lake would drain in to that area right in between it, which is kind of fascinating. He just describes that as one of the most amazing things that anyone could see, even among lava lovers, right? And so, but check this out, August 1911, right? The previous picture was July. In August, this thing is sinking, and it sinks over the course of, about a day, right? Here's 10:30 a.m. This thing is sticking out of the lava, right? And picture from 5 p.m. And there is still a little tip of it sticking out, but all this hotter fresher lava, we can tell it's kind of just from the texture of it right here, even as a black and white picture. It's all coming up to replace it. Right, so that's really fascinating. You know, that this thing was up there, was floating that whole time for however long, and then it got eroded from below. Lava was kind of pouring into it, and eventually, like, it got compromised to the point where it sank. Believe it or not, like, you know, whatever was you know, whatever structure had to hold it up, it wasn't able to sustain it, so it actually sank in there. And even more fascinating, let me advance it here, is that he describes a great inflated cylinder of black glass which formed over the sunken island, right? So as the island kind of drops into the pit, whether it's the gases or whatever that's, you know, trapped in there, you have that same kind of lava encasing gas feature, right, forming over the island that he actually describes drifted against the surface current as that sunken island got pushed across the lake, which is kind of crazy to think about. Right, so let me keep going here because he's got a lot of these. I don't want to spend too long. And then after that thing sank, then a couple of other islands, because of the chilling effect of the mass, form above where it is. So you actually have like secondary islands formed because of like the cooling of the lake in the spot where the thing sank down, which is kind of shows, you know, just a little glimpse of the crazier things that can happen there. And so Perret has a diagram that he put out, you know, in 1913 of how he imagined this mass actually happen, right? Because he's imagining this deep source right here. It's kind of this bubbles, and I'm going to change my color again so it's more visible. Right, these deeper bubbles right in here coming up. That's kind of the deep source, like the more coalesced bubbles are coming up, and like this is a source that might have been underneath that middle of that island kind of thing, right? That was kind of eroding it and kind of allowing space to collect in there that lava could later pour into somehow, right? Maybe that's what cracked it from below and allowed it to kind of start to sink in the first place. But you also have all these other little dots, or all little bubbles of lava that are kind of they're in lava, but they're not big enough to actually cause a lava to just purely go straight up. They can actually get pushed to the side and get deflected by the circulation that's happening within the pit, right? And so the bubbles are coming and not going straight up, but they're actually taking a right turn, flowing along what might be counterintuitive, the edge of this crater, right? And the shape of this crater, by the way, was, you know, described by visitors to the volcano house. You know, we had surveyors coming up, and they actually came up and they would take occasional surveys of the pit. And it turned out that in, I want to say 1902, after a big draining event, the surveyor came in, they surveyed, and this is the shape of the pit. So this is not made up. This is actually the shape that they saw this thing to be, which then later refilled full of lava to the higher level right here. So he knew that was the shape of it underneath. So you could then try to infer this kind of flow, right? So once lava comes to the surface right here, you could have an upwelling site somewhere over here, and then you have a movement of the crust from one place to the other, right? This is different from what we have now, because now we're having a lot pouring from above, but this is how we have to start, is by, you know, what we know in the past. Now, and as the stuff goes to the other side, it's have a chance to form crust, and that crust then is what's sinking, right? You know, once that first crust starts to tip over and lean into the lava, it's going to go in lengthwise. It's basically got a shape like a big slab. It wants to sink. Or if it's in a shape like this, it probably doesn't want to sink until that spattering happening at the edge here, where this thing gets pulled in, because there is gas that's got to come up, whether along the side or from stuff getting pulled down, comes out of the spatter zone right in here. The slab breaks, it's able to get tipped, and it starts sinking. Once it sinks, then all the material that's sinking in forces the convection and forces the circulation in the lake. So you kind of have two things happening, right? And it's big question marks right in here. How much does this stuff mix going back in? That was impossible to tell, and a lot of times it still is impossible to tell unless you go and do the chemistry studies of, you know, what's up here and what's down there, if it happens to erupt out of some other crack, you know, something like that, you know. So that's the situation here, you know, and this is, you know, back to 1913. I'm going to show you guys, you know, there was a Kīlauea lava lake eruption in August 1963, and that's going to show you guys a source for that. And they have a very similar diagram where they have bubbles coming up, gas charged lava coming up one side of this crater, forming that crust. In this case, it's flowing in this direction, but their circulation goes back around over here too, right? And they're showing maybe you cannot see with the resolution here. There's quite a bit of gas coming out the side and spattering off the side here. They're actually showing there's actually topography, like difference in on the shape of the surface of the crust of lava, even during the eruption, right? Higher on one side than the other. That's what they saw there, right? And after everything actually drained back and settled, they ended up with a shape that looked like this. So whenever this eruption is over, we won't be surprised to see something like that happen too. The crust sagging and settling and possibly collapsing in some places to have a different shape than you actually see it nice and smooth and flat now, even with all those little wiggles and bumps and islands in it. Right, so that's another example from 1963. This, more recent, 2016, right? Very, very, very similar thing going on here, right? They're actually getting a little bit more complex. Is a couple just one way, going up and in, right? Or is there actually more of a intermixing happening as well, and mixing happening in a zone over here? Or is there something crazy we just can't even imagine, happening in the middle, where it's like just this is happening over here, and totally independently something else happening in the middle, and who knows what? And to kind of answer, well, what about who knows what? Well, here's another model. This is from 2008. Someone considering all the possible things that could be happening on a lava lake, right? Surface motion in both directions from a spreading center, stuff dripping down, stuff collecting on a lake floor, stuff oozing back down the throat of the thing, right? Gas and gas-rich lava and hot lava trying to come up, and then how all this stuff interacts, right? That's the big question mark of, well, who knows what in the middle right there, right? Something, there could be all kinds of complications that people are trying to figure out, but as you can see, there's a lot of complexity there. So the source for this particular image is Andy Harris's model and GRL here, 2008. And that previous one, we'll talk a little bit more, is Matt Patrick, Tim Orr, Don Swanson from USGS, and also author from Lamont Doherty, last name Lev. So kind of want to show you guys what the modern version of this actually looks like without kind of dwelling too much on all that. Kind of give you guys a little hint of what happened in the past. But what we had during the Halema'uma'u lava lake was a camera at the edge of the crater, right? It looked like this. Here it is, pointing at this lava lake. And of course, nowadays we're way higher tech. We should be able to do a lot better than that. And we actually had a lava lake flowing. So I'm going to jump right to the panel. This is what the USGS may have available to them internally, is a dashboard that shows them based on images of a lava lake, which they compile roughly every 15 seconds or so, right? They want it to be like, if you wait too long between images, you can't really track where everything is moving. But this is an image from 2016, right? Showing lava lake upwelling at its north end. I need to change my color again here. This thing's too red. Upwelling at its north end and then flowing to the south, right? In this particular live reading, so to speak, right? Not only that, they actually have flow velocity over the past month, right? How fast, and they actually have it split up into spattering regime and non-spattering. We'll go into that in a little bit of detail, not too much later. Azimuth, which direction is it flowing? It's all flowing, to the southeast during the past month over here. Where has it been upwelling? Right over there, right? This is all automatic. MATLAB scripts and other, system scripts, analyzing thermal imagery automatically and making these vector maps of the way the surface is actually going. Not only that, they can, they're measuring area of spatter, right? The speed of the plates moving through there. The direction of movement is plotted in a different way over here, and this plot over here is actually the tremor of the volcano, right? So we're looking at before, how much blue ink. This is actually a measure of it, how much tremor. So if this goes up, it would be like more ink, and less ink. So that kind of corresponds to gas output, right? As we just described. So proxy for your gas output, right? This is the past day up here, right? And then you can zoom out, and this is a past week down here on the right. Same kind of thing. So you can kind of see what's happening now and what's happening in the past. And so I won't go into that particular plot right there, but I'll show you that they also have things putting out. So this is an example. Every hour they have an automatic output of what was it like this hour? What was it like this hour? So you can imagine if they managed to get this up and running on the current lava lake, which I would be surprised if they hadn't, they can actually see which way the lake is actually flowing based on the thermal maps automatically generating. We have to kind of infer from every 20 minutes or every hour kind of imagery, right? And it's much harder to do that as opposed to every 15 seconds. And so that's why we still have some uncertainty and ambiguity, whereas they could probably ideally at some point we'll release some of this imagery for this current eruption, and we'll see, oh yeah, clearly it's backflowing over here, and clearly it's not backflowing these eras, and it changed at these point in times, and you get a whole history of the whole thing going on, right? This is an automatic 1-day, 24-hour panel that's put out by that software they have running as well. So kind of to go into a little bit more detail, they find times, right? So this is kind of that north end, that deep core of it's underneath this side. So upwelling lava is coming up, hitting the surface, and then spreading to the south and going back down. And so there is spatter down here going down and in, but well, not in this particular image. This is non-spatter. So it's just kind of convecting up and over and going down and in, right? Kind of straighten up and over. That's kind of case A. Case B, it's moving in and it is spattering. Got ahead of myself right here. In the southeast, upwelling in that same area, right? So they're still calling this normal flow, even though there is spattering happening. It's happening where you expect it, where the stuff's going back in and where the crust is tipping back in and circulating back into the lake. Now, occasionally, they see a reversal of the flow. The flow starts going from south to north. And you see spattering where it sinks in at the north as well, right? So these are the times when it's reverse and more chaotic, and what they're calling more unstable, right? So, for example, once you have those kind of labels, you can then go through your image, hour to hour. You can say, okay, this one is non-spatter. This one is spatter reverse. This one's spatter reverse, spatter reverse, spatter reverse, non-spatter, non-spatter, spatter reverse, and that way you can kind of track how things are going over time, and that's how they figured out, that basically when you see your upwelling, what they're calling a stable upwelling driven, even with spatter, or unstable, a spattering driven, when essentially upwelling is not happening, and you're able to convect this thing back across where it normally would be coming up. So they can then tie this to area of spattering, right? So like they basically have here different regimes. So I'm gonna maybe skip over this one because it's a lot of things to look into. Then, and this one's a little more easily labeled, where you have these kind of darker columns right here as the stable, right, and then in between as unstable, stable, unstable. So while it's stable, the spatter area is kind of constant, and when it's unstable, it kind of is spiking up, right? The temperature is steady when it's not spattering, or when it's even stable, non-spattering. But when it starts unstable, then you start to see the temperature doing its wild fluctuations, right? The velocity drops a lot when it's unstable spattering compared to before, right? So all these different ways that they analyze direction, how it flips direction, number of plates, right? Elevation of the lava lake, they can compare that sometimes too, right? Okay, if the lava level is going up, lava level is coming down, lava level is going up, lava level is coming down, right? That kind of cyclical pattern you expect from a degassing, the pistoning, right? In this case, the source was below, and I was just able to just kind of keep feeding continuously for all those 10 years while still feeding the pool eruption. And it was that still excess buildup is why we got the 2018 eruption, right? So tremor as well, right? A lot more tremor during unstable spattering, right? Elevation levels drop. That kind of thing is something that they can determine, right? So same kind of thing there, right? I'll kind of skip over that. I kind of went into that enough detail. And this one I showed earlier, you can kind of correlate the tremor to spattering or not spattering, right? Things that can be useful for us to analyze today. And they can kind of group all the different images and kind of do a statistics analysis. And this is basically what they come up with, this kind of plot, right? Like, how different flows of the plates, the direction of flow, and all of that. So I'm not going to go into too much detail, but you guys can go over that paper. But from all that, they basically can come up with more models like this, right? We still have our basic model of upwelling on one side, coming across and sinking down, and then something happening in the middle, right in there. And then we have spattering happening sometimes. And then when the lava level drops and we have spattering on this side, then we have that kind of, essentially no upwelling going on because we're having gas pistoning. The gas isn't coming up through an upwelling. It's kind of building up its charges down there before it can resume that kind of upwelling once again. All right, so and that's a lot of detail there, but this is kind of just, small bubbles, large bubbles, same thing as before, gassing coming out of the surface passively, and as well as spattering. They have all these details. They talk about how there's actually, you can see the surface of the lake rise when you see the upwelling, right? They can actually measure this on a lidar. and you can see it sinking in when you have spattering flow, right? These are all different things that can then use different techniques like the LiDAR or different laser rangefinders to try to measure these differences and quantify how much and what's going on in there, right? And you actually have a whole flow chart here, right? Like, how does this actually all go together? Well, if some of deflation, lava levels drop. Some inflation, what happens? No triggers, or thermal gas pistoning. Well, all these things can cause spattering. And once spattering happens, then you reverse the flow, it gets unstable, increased gas relief, increased tremor, drop the lava level. Right? That's kind of all goes hand in hand. So you can see that these patterns are quite fascinating, how they are able to kind of piece it all together like that, right? And so they can correlate tremor, spatter location, and lava levels all with the surface flow, and we see on the surface right there, right? So since today we can only see the surface of our lava lake in Halema'uma'u filling in, we can kind of try to assume circulation based on what we can see and what we've learned from these kind of studies, right? So that's a fascinating thing there. So, that's kind of where I'll leave it. And before taking our last round of any final remaining questions here, just to show you guys, like, how that original model, let me go back all the way to this one right here, diagrammatic section, of the lake, right? So, there's one more thing I wanted to tell you, kind of get back to the story of this island to kind of finish it off here, right? Once this black cylinder formed, right? Let me see if I can find the passage here, right? That Pere describes what actually happens after this thing sinks in here. So the sinking occurred at the east end of the lake, and the cylinder at once began to make its way westward against the surface current, it being towed by the mass of the island suspended in a west flowing undercurrent, right? So I can jump back to, where was it? Where was it over here? This one, right? The lake is down in here, and it's getting pushed this way. So its float that's up here, sticking up, is moving against the surface current. Right, does that make sense? I'm drawing in red here. The island was submerged in here. It's got its float sticking up here. It's getting pushed from below in this direction. And so the whole mass, including this upper float, is moving against lava that's moving around it, and the surface current going in this direction right there, right? That's what he saw, right? So the island got pushed all the way over here. And then what? Well, they actually saw this island pop back up out of this lake, right? And so let me see if I can find a passage of that. Nor is this all, for on approaching the west bank, the sunken mass was again brought to the surface, a point of the original island being seen and photographed emergent from the lake. This reflotation was no doubt caused by the rising gas-charged lava current of the west end, and no sooner was it accomplished when the whole system processed eastward again, being now entirely under influence of the surface current. So this thing did a lap, right? It went all the way up, went back over, and then it went back down again. Right, so fascinating to imagine how that's really the best example we have. And so that's why when I see the USGS reports of how high is the island level above the surface of the lake, that now means more, because now we can imagine, okay, that can actually be a signal of what's happening as far as it being pushed up by buoyant gases, or being pulled down by any kind of downflow, or is it just being pushed by the side, and what's the current pushing it? How deep is that thing? What kind of route does it have, and how's it getting pushed from below, right? Or spinning around if it's getting circulated around, right, at some lower depth. Like, that's what that motion of the island can tell us. It can tell us, like, if the thing is rotating counterclockwise, you must have some counterclockwise flow at the depth of the root of that thing, right? We can go all the way back to our time lapse going on right now. What's going on with our lava lake in the last 24 hours here, and the island moving around, right? We're seeing this island. I gotta go back to my yellow color now. Seeing this island now moving this way, but it was also spinning a little bit, right? Which you'd imagine, if there's a counter current at its base, as lava that's sinking down in this area right here is trying to get out of this hole in the drainage out of the north vent right over there. Right, so there you go. That's, I've tried to answer, we had a lot of questions like what's happening under the surface, the circulation, where are things going, what does it look like underground, right? That's the basics of it, with the kind of big question mark of, is there another drain down here, and is there another drain or two over here as well that could possibly be taking some of that flow and feeding it back in, right? And if this lava lake lasts long enough, then we'll have the pleasure to see what happens to this island as it evolves over time, and maybe some of these smaller ones before the bigger one might do something too. So we'll keep an eye on that as well. All right, so questions before we wrap it up here.
Final round. Noel from Kona site asks, do you have any projections for how long this is going to go on? Got used to the beautiful air for the last 2 years. First time in 40 plus years we had clean air consistently.
Yeah, we don't really know how long it's going to go on. It's all about, if I go back to the, I really would like to see more of the sulfur data, right? If I see this right end of this plot keeps going downwards, or if it's going to stay long and drawn out like this, right? And so we haven't passed a threshold below the previous eruption, when for 10 years the air was bad in Kona, even at 2 to 4,000 tons per day coming out, right? So if we're at 3,300, we're still in the same range. You're like, well, okay, it might be low for you guys, but it's just as bad as it always was, so I totally understand the concern there. I have no idea about how long this is going to draw out, but what I would look for is the SO2 measurements as the indicator, as our proxy for the flux, right? More so than actual different kinds of venting coming out of the actual vent itself, whether it's Strombolian and more gas charge or less gas. Like more so than that, I'm looking at the actual total SO2 emission rates, out of the whole lake and out of the whole system over time.
All right. The next one is from Carl from Pearl City. He asks for you to comment on the recent Mauna Kea earthquake and what does it mean?
Okay, the Mauna Kea earthquake. Let's see if I can get it over here. It is this one right here. All right, so this earthquake, if I click on it, I know you guys can't read this over here, but maybe click on it. It'll give us more information that maybe you can tell here. Right, so this is showing magnitude of 2.1. I'll zoom that in as much as I can. It's showing us a magnitude of 2.1 and a depth of 33.9, 34 kilometers essentially, right? So what is that, like 24 miles maybe, somewhere in there? 20, I don't know, somewhere in the 20s, mid-low 20s.
It's deep.
It's deep, yeah. So that is essentially below the mass of the volcano itself. It's kind of in the crust, right? If you imagine Hawaii Island's on a plate of ocean crust that is kind of sticking up and through, right? And actually pushing it down. So Mauna Kea does it also. It's actually pushing down the oceanic crust that it's on through its weight, and it's sinking back down as the whole mass moves away from the hot spot and cools and contracts and kind of wants to go down and wants to contract. Many people, I don't know, used to be, I'm not sure anymore, date myself now, right? But there used to be you'd have your science chemistry class, you have your Bunsen burner and your piece of metal. You put your metal over the Bunsen burner and you see it kind of heat up and it kind of start expanding and point up when you have two different metals on two different sides, right? One expands, one the other kind of thing kind of curves and points up, and then you take it away and it kind of cools down and it straightens back out again, showing how how materials can expand and contract and at different rates, right? So the island itself does that, and so do the mountains, right? And so moving away from the hot spot allows a long-term kind of cooling effect and sinking effect. That's something that's seen across the whole Hawaiian island chain. That's where the massive Mauna Kea sits on, and just the weight of it causes adjustments as well. So as the whole thing is moving and tipping and settling, you have earthquakes that happen. And so that one is really not that interesting, honestly. It's just kind of a regular background settling in the island kind of earthquake, right? Now Mauna Kea, maybe another update we can talk about. Mauna Kea does have periodic earthquakes, something like every 12 minutes. It has this very, very constant signal that's going on for years. Like that's way more interesting, this kind of thing, even though it's kind of a smaller signal. There seems to be like some kind of other process in the mountain with the cooling of the magma chamber and gas separating all of that. So the volcano, there's still magma in there, but it would take something drastic for it to come out. However, geologists classify volcanoes as active if they erupted in the last 10,000 years. And by that definition, Mauna Kea is active and dormant, as is Hualai, active and dormant, as is Mauna Loa, active and dormant, as is Loihi, active and dormant, Kīlauea, active and erupting. Kohala, might call that one extinct. But extinct doesn't mean it will never erupt again. It just means it's not gotten to its rejuvenated stage, right, where it possibly can erupt for different reasons and different forces, different priorities, and different process of how it actually happens, right? But you basically can kind of peel off enough stuff above it to induce the buoyant magma that's left, even though it's kind of cooling, to come out. So you can have kind of spot eruptions, right? Things like Diamond Head on Oahu, or other submarine eruptions offshore Oahu, and things like that. So that's a whole other geology lesson for a whole other day, and there are people who are more qualified to talk about that than I do. I kind of focus more on an active eruption here, but that's kind of the background of it, right? There's nothing magmatic happening in there with that particular earthquake, but there are kind of other more subtle signals that are kind of just long-term cooling and that kind of thing, until it next awakens again, whenever that may be, right? You might ask, why 10,000 years, right? So 10,000 years is kind of an arbitrary number, but it's more or less what the average between eruptions, it's an average like maximum length between eruptions. And so one analogy I've often used in the past is, if I were to come upon someone who was passed out on a road, for example, and I wanted to try to detect if they were breathing, right? A person breathes, you might take a breath, I don't know, maybe an average maybe once a second or something. So if I show up and I wait a half a second and I don't see a breath, I shouldn't be like, oh my God, he's not breathing, it's dead. I just haven't waited long enough for the typical length of a breath, right? It might be a second. So if I've waited 2 seconds, 3 seconds, 4 seconds, there's no breath, then I might be like, oh, the person's not breathing. Right? I have to wait long enough based on a period of activity to make the interpretation. And so for volcanoes, that period of time is 10,000 years. And so if it goes 10,000 years without erupting, then we're more comfortable saying, okay, now it's past that active phase, right? And that's why that number, if you guys are interested in the background of that. So just background settling on Mauna Kea.
All right, so I'm going to do one more serious question, then I'm going to have some fun with you.
All right.
Kind of following up on your talk about the formation of the island, and this is kind of just like, I think, a yes or no type of thing. Is the lava island connected somehow to the lava pouring into the water lake at the beginning?
We totally think so, yes.
All right. Now for some fun ones.
All right.
Do you have, where the earthquake swarm is, could that section of the island break off into the ocean and cause a mega tsunami? This is like the Helena slump YouTube hype that we hear about, it's constantly.
Okay, so where the earthquake was, that's what they're saying.
I'm not sure if they mean Pahala or the summit or the south flank. Could be, pick one.
Right. Okay, so let's see what layers I have on here. Maybe I can do that one, yeah. So, I mean, there are areas, so the background of this is there are areas of the Hawaiian Islands that have kind of had collapses in the past, right? The most dramatic ones of all of these, if you look at the North Shore of Molokai, right? This is Molokai right here, Molokai Island. And you can see it's got the tallest sea cliffs in the world on this north side over here, Kalaupapa, famous, and we won't go into all that. But on the seafloor here, you see big chunks of debris, right? Some of these pieces of land are really big and have traveled intact a long way from their presumed source over here. So there are times when there have been big collapses of Hawaiian volcanoes, right? Now we don't know like how fast all this happened and all that, but the speculation and the basis of this idea is that these extremely infrequent events, when they happened, has to happen. This has got to be moving pretty fast to get all the way over there, right? That's like, I'm not sure how far, but right, if our island's 90 miles across, we're talking about somewhere in the range of that, 90, 100 miles away from Molokai, right? And so there are other areas where you see evidence of that. They're kind of other kind of submarine fans, as they're called, and other parts. There's some kind of on this very steep Kalakakua part of South Kona of Hawaii Island, right? And however, on the south side of Hawaii, over here, we have Loihi volcano right over here, just offshore, because of the hotspots over here in this direction over here. So it's a lot easier for this island to collapse, land off of this side, for example, right? You can kind of see that slope right there, this slope over there, right? Than it is to collapse over here, because you have this big volcano rising 9/10 of the way from the ocean floor to the seafloor. You have this big seamount over here. Maybe it's not quite touching, right? But you see there's other stuff that's kind of in a way. This is like a big backstop right here. And so you could have more localized. If we kind of zoom in here, we do see fault lines. This is the Helena fault right here. Maybe I should change my color one more time here. This is, what we call a poly, the cliff sides. You can kind of see these are all different cracks, right? Where it has a big pattern of the southwest of the volcano is over here, right? And so if I were to take this in a cross section, the surface of the volcano is going down, and you have a crack going like this. You have other cracks going like this, kind of feed into it, right, at different levels. To kind of allow this piece of the island to move to the south and kind of slump in, right? But geologically, a slump is a slow-moving motion of land, and like not an earthquake. Like those are usually different kind of things, or it can refer to the actual piece of ground that did the moving could be the slump itself. So there are different ways to kind of term that, right? But so it's unlikely here that you have this configuration. You have anything here moving and collapsing way off on the island over there, right? So you see we have much steeper shores over here by Puna, right? But there's no reason to believe anything's going to happen there either, right? Because we have this big ridge that moves off to the east. It's like a big spine. Right, this is the submarine East Rift Zone over here, offshore Hawaii Island. That kind of gives structure as well. Here's an older submarine East Rift Zone in Mauna Kea. You guys are curious right there. So all kinds of interesting things happening here, over here. So you certainly can have collapses, landslides and pieces, of the island kind of calve off, but we don't see any evidence of that anywhere now. We would see earthquakes happening in the areas over here as well if we're going to see activity like that, because all that rock is cracking before it's going to move, right? We would see our satellite images that do INSAR would see the ground shifting and settling and slumping in big areas like that. So we actually can use satellite nowadays to do landslide monitoring and ground stability studies, and so that's a big thing we lean on, and why we shouldn't expect something like this to kind of happen out of the blue in the future. We should probably see some kind of signal coming ahead of time.
All right, and I'll check it one more time, but into the final question, preliminary final question. Could there, talking about, been seeing it a few times, people pointing out like, oh, there's X amount of new eruptions taking place, right? And they're trying to make some connection. Could there be a massive amount of pressure in the Earth that's causing these eruptions from some event in the Earth core, or sunspot, or planetary alignments? We'll go with that one.
Right. There's a lot of things that you baited me with there, right?
It's a big question. Don't worry.
Yeah. There are a lot of different forces that are at play within volcanoes, but generally speaking, the force it takes to break rock is massive, and the force that it takes to build up and kind of cause an eruption is massive. And so if you have like an open vent to the surface, it's been documented in the past that you can see tidal effects on lava lakes, for example. That's something people have talked about for a long, long time. And you can, you see tidal signals on the Earth itself, right? If the volcano, let's say it's like all the way primed, ready to go, and it's just looking for that last straw, right? Literally the last straw to break the back, then maybe a tide could be it, but it has to be all the way primed and ready to go, right? So it doesn't do that over the course of one day. And so maybe if you had a volcano that had already gone through months of inflation and earthquakes, and already gone through an intrusion, and already gone through all of that, and then suddenly the tides were was ready to go within the next 6 hours, and the tides are optimum, maybe that helps it trigger at that point in time. That's possible, but only as a trigger when it's already at that kind of tipping point balance. It has to get to the tipping point through its normal mechanism. It can't get to a tipping point through just the tides themselves, right? That's kind of like the last question. We're working our way backwards, right? So as far as solar effects and earthquakes are kind of a topic of, discussion nowadays, right? And a similar kind of thing, right? It does seem like there are electronic disturbances associated with earthquakes. It seems like those disturbances may be influenced sometimes by solar effects. And maybe same thing, if you have a fault that's like been building and priming pressure for a long time and it's getting ready to go, and suddenly it's ready, it's going to happen any time now. And then maybe when you have that extra solar charge or solar connection, maybe you can, and that can be the trigger for it as well. That's kind of a theory that's going around, and we kind of have to go more into the details to really give you basis for that, right? But there are some associations being made, at very general terms with that. Other planetary alignments, if you can measure the extra tidal force of those extra planets on Earth compared to the sun and moon, you probably see that, once again, maybe if you needed that extra whatever a little bit, like, the extra grain of sand or something to put on a pile to like cause the whole thing, maybe that could be it. But, on the scale of it, those are very, very small forces compared to the forces the magma is moving through the Earth, pushing the rocks around, moving the whole south flank of the volcano, like pressurizing all that. Those forces are much larger. The actual root cause of them is not any of those things. Those things could be triggers, but not the actual roots. As far as everything happening all at once, no, there's always volcanoes happening, always eruptions happening. I don't know, somewhere between, I think I've seen as many
10,
as 20. Sometimes 24 at a time, but like
it looks like more 10 20 right now.
Right. So, it's typical to have volcanoes erupting across the whole planet, and we can maybe go over this again, and we've done this in the past updates, but maybe we can do it again. It's been a year or two. Go through that someday and show you guys other places that are erupting as well. Just kind of cursory look so you can see like how many different places typically erupt, right? Everything is connected within the Earth, and things do feel each other, but you gotta remember that the mantle of the Earth moves at the scale of centimeters per year, right? That's about as fast as your fingernails grow. That's the tectonic motion on the surface of the Earth. So for the transfer of pressure from one place to the other, right? Like it's not something that one day this place is affecting that place, affecting that place, affecting that place. It doesn't go like that. You can have you have a ring of fire, as it's called, to much to some people's chagrin. You have tectonic and volcanic activity around the whole Pacific Rim, kind of in a pattern, because that's where the plate is coming together. That is the expression in real time, in real geologic time, of them interacting. It is that, and it is volcanoes erupting. That actually is it. As far as one triggering another across the Earth, that's highly unlikely, right? Maybe energy can travel across there faster in the form of earthquakes, but you can't move the heat, you can't move the pressure and all other stuff nearly that fast across the surface of the Earth, from one side to the other, all of that, across all of different stratification of, outer core, outer mantle, inner mantle, outer core, inner core, all the different layers. There's nothing there's distinct boundaries between those things that we don't see. For example, between a core and mantle, any real mixing, right? At least from the seismic signals that we have, which, granted, isn't the best magnifying glass, since you don't really get to see it directly. So I threw out a lot there, and maybe that appease some of the people, right? It's interesting. What could be a trigger for an eruption? But any number of things, right? There have been there's videos out there of a lava lake surface in a pit, and people throw in like organic waste, and it breaks the surface of the lake, and essentially induces a little eruption by someone throwing something into the pit and break that crust and kind of cause on a small scale. So there's all different ways to trigger things that are primed to go. That wouldn't happen if you just threw that stuff into a more solid crust lava lake. It's got to have a thin crust, have gas built up underneath there, and once you puncture it, and suddenly you can induce all the overflow, overturn, and all the gas coming out. So all that kind of stuff.
All right, we got some more questions coming in. I'll cut it off and just call it 2 more.
Okay.
I think these are both good questions. Just Ducky on YouTube asked about the new land at Poiki, what we call the Delta out there, and the boat ramp area. How stable is the land out there, the new land?
Well, so at the very, very edge of it, the cliff itself is already being eroded and kind of broken down, right? And that's expected. If you look at the whole coastline of the island, it's mostly rocky, with only a few exceptions of where the land kind of can sink in, or the sand collect, and combination is just right. So you do see that kind of thing calving, right? But as far as the structure of what's built out from before, we remember seeing data from I believe it was the MV Nautilus, right? That did the underwater scan, and it showed like something like 400 million cubic meters of lava had erupted underwater. Like something like 1/3 of all lava erupting, or half of as much as what erupted on the land, also went underwater, right? So there's a huge amount of land down there supporting it. It's not floating, and that stuff flowed in, and it was was probably able to solidify and be pretty solid down there, and certainly had some kind of landslide and debris things, but overall I imagine it to be pretty stable. Maybe not the very, very edges, and maybe there might be some other areas we might see here and there, show signs of settling or sagging, but as far as I'm aware, it's across the board all pretty stable. More of the settling you see now is from the cooling of the lava inside of that core, as the whole thing cools and contracts and settles and cracks apart. Yeah, in that sense, it's changing.
One thing that Nautilus really showed was the angle that it was, at the lava flow down to the seafloor, the angle of repose, which is, what is loose substance's stable angle if you were just to pour it, basically. Mm-hmm. What is the angle that it can be stable at? And the thing that we've been seeing more recently down there is the similar to all the eruptions that have gone into the ocean that I've seen, is it goes out and it makes it more, you see lava lobes and things like that going into the water after the eruption ends, but then years and years later, like if you go down Kapoho, it's sea cliffs, sheer 90 degrees straight down, cliffs going into the water, right, with no clear access to it. So it's transitioning in that way, but those are very localized collapses, and then they get washed into the Poiki Beach, which isn't a beach anymore along the shoreline. It's now just, different sizes of rock, basically all throughout that area. So that's kind of really where we're seeing down there now. Haven't seen any, like collapses or anything along those lines, like a bench collapse, but yeah. Final question. Are the seamounts that are around the south of the island, excluding Loihi, have anything to do with the hotspot, or are they from a different process?
Well, they're not from our hotspot now, right? They're from some probably similar process, but that happened long, long ago in a far, far away place. And so those are, a lot of these come from the Cretaceous era, right? When the dinosaurs were roaming around, and there was a lot of undersea volcanism in the Pacific Basin during that time. And so I think of it as almost like, you get like, you have a canvas, and your canvas has some imperfection in it, right? Maybe it has a different, slightly discoloration here or there, right? And it's basically it's part of the background that the hotspot's erupting onto, right? But it does have the remains of previous seamounts of eruptions, and that happen underwater at other places in the Pacific Ocean, basically. Yeah. So,
all right.
Thank you guys for the questions. Yeah, we'll
end it off with we're going to go through some of our donations that, make this show and what we do on Hawaii Tracker with our write-ups and everything, able to manage the time commitment for it. 1 second here. So yeah, these are our thank yous. These are the supporters that have been able to, keep us going. The Bill B, Jana K, Ali K, Deborah M, Ashley C, Connie W, Patricia C, Elena J, Katrine G, B. Reynolds, Francis D., Jan R., Kim B., Nina S. I know her. That's my aunt, Nina Stone. Nancy M., Deb B., Jeremy B., and Craig L.
Thank all you guys.
Teresa H. One more. And if you guys want to help support us, like the people that we're naming off, the best way to do that is on hawaiitracker.com/support.
Yeah, and we do have advertising for those of you guys who want to help us out in that way as well. And we do post all of our updates on that page, right? So if you don't want to go digging through, whether it's Facebook or YouTube, wherever else, it's easy to find that at hawaiitracker.com, right? And apologies if we mispronounced anyone's name, Deborah or Deborah, or all of you guys. Yeah. We love all you guys. Thank you so much. Yeah, appreciate it. So with that, you guys, mahalo for joining us. And I've kind of had a longer update. We plan to get back to you guys after the new year, unless something dramatic happens. Our next update will probably be January 2nd. We will be posting other shorter snippets in non-video form, in the meantime. But thank you guys for joining us. Mahalo, everybody. Happy New Year. A much better 2021, 2020, I hope. Aloha.
Aloha.
So for myself and Dane DuPont, aloha. I'm Philip Ong.